So let's talk about another equilibrium constant that we run into. Water can undergo something called autoionization. And basically, what happens is you have two water molecules, and one acts as a base and one acts as an acid, and it will form a conjugate acid and a conjugate base. And so we have H3O plus here and OH minus. Now, when we look at this, these waters are pure liquids. So when we do this equilibrium concentration, we don't include them. So we can just cross them out here. And so this equilibrium is based on the concentration of H3O plus and OH minus. And at 25 degrees Celsius, which is all you're ever going to see, that is going to be 1 times 10 to the negative 14th. So that means in pure water, the concentration of H3O plus equals, 1 times 10 to the negative 7th. And then the concentration of OH minus also equals 1 times 10 to the negative 7th. Now, if these vary any, we can use this equation and this relationship to determine the concentration of either of these. And so this would be something worth committing to memory because you're going to use it. So let's look at different ways that we can use this. One of the things that we're going to see, right, is in an acidic solution, you are going to have more H3O plus. Now they're using H plus here, and so it's important to understand that some references are going to use H3O plus and some are just going to use H plus. Those are going to be interchangeable. So if we have a higher concentration of H3O plus, we're an acidic solution, we are going to have a lower concentration of OH minus so that they both balance out to give us 1 times 10 to the negative 14th. If we look at water, the amount of H3O plus and the amount of OH minus are going to equal each other. When we multiply these together, they still equal 1 times 10 to the 14th, negative 14th. Then when we come over here, in a basic solution, we have more OH and we have less H plus. And when you multiply these together, you still get 1 times 10 to the negative 14th. So we can use this relationship if we know our OH and that these multiplied together equals 1 times 10 to the negative 14th to calculate the H plus. Now, one of the ways that we measure acidity is using the pH scale. So in the early 1900s, there was a Danish biochemist named Søren Sørensen, and he proposed this scale to express the acidity and basicity based on the potential of the hydrogen ion, right, as measured by an electrode. Now, people think that the P in front of the pH stands for the potential of hydrogen or the power of hydrogen. We're not really sure. I think those are really good kind of guesses, but we're not really sure why he chose pH, but that's what he chose. And he said, all right, look, pH equals negative log of the concentration of H3O plus. And H3O plus can be huge. It can range from, 1 times 10 to the negative 18th all the way up to 18 molar. And so the pH scale for us, what it really does is reduces the numbers so that it's a more manageable way for us to understand and quickly reference things that are acidic versus things that aren't acidic. Now, he also said, look, you can figure out the POH, which is the power of hydroxide, by doing the same thing, negative log of the concentration of OH minus. Now, I want you to be aware that if you need to solve for the concentration of H3O plus, you are going to take anti-log in your calculator, which is going to be a 10. So it's anti-log, which will just be the second button in a lot of calculators and log, and it's going to look like a 10 to the x, and you're going to take 10 to the negative pH. Same thing with OH. If you have to solve for the OH concentration from the POH, it's negative 10 raised to the negative POH. Now, we also know that the KW equals 1 times 10 to the negative 14th. and that equals the concentration of H3O plus and the concentration of OH minus. And through a process, which I am going to represent here as math, right? We know that if we take the KW, right, that we can also get a log form of KW as well. And so we come down here, and that's our PKW, okay? And when we do that, we take the negative log of 1 times 10 to the negative 14th. That gives us 14, and that equals the pH plus the POH, right? Now, we can use all of these things to calculate pH, kind of depending on what we're given. So what we're going to see here is there's multiple ways to solve a problem, and you may solve a problem different than someone else and still get the right answer. So when we look at this, I want you to notice here, things above 7 here are basic. And then they have a higher pH, and things below 7 are acidic. They have a lower pH. And then 7 right here is neutral. So let's do an example. What is the pH of a 0.040 molar solution of HClO4? Now this is a strong acid, and we solve strong acid pHs this way. So here, pH equals negative log of the concentration of the acid. And we're just going to use H3O plus to tell us that, and that's to represent that, and that's negative log of 0.040 molar. And we put this into our calculator. So the way I have to put it into my calculator is I enter this first, I hit the log button, and then I have to take the negative. And that gives me 1.40. Now, if I wanted to find the H3O plus concentration from 1.40, right, I would then use H3O plus equals 10 raised to the negative x, and I would do 10 raised to the negative 1.40, and that would give me 0.040 molar. My suggestion is to try this in your calculator right now, right? And let's make sure that you know how to use your calculator to get these two values, and if you don't, I can help you with this. Now, some people love charts and graphs, and so this information just summarizes what I've talked about, which are all the different things that you can calculate. So you can calculate pH, POH, OH minus, and H3O plus, okay? And it gives you different pathways. So if you need to go from H3O plus to OH minus, you can use this relationship here. If you need to go to OH to POH, use this relationship here. If you need to go backwards, you need to take the anti-log. Same thing here. If you have H3O plus and you need to go to pH, you can use this equation. And then if you need to go from pH to POH, you can use this equation here. So all of these equations are useful, and if you're more of a visual learner, you might find that to be really helpful. So I want to do one more example. What's the H3O plus and OH minus concentration of household ammonia, an aqueous solution that has a pH of 11.70? There are a lot of different ways we can do this, and so what I'm going to do is I am going to start with my H3O plus concentration because I'm also given the pH value. And so I'm given both of those, and I'm going to wait on OH minus. So I know that I can find the H3O plus if I take the anti-log of the negative pH. So I'm going to fill in the negative 11.70. So when you put that into your calculator, you should get 2.0 times 10 to the negative 12th molar. And that's our concentration of H3O plus. Now, we need to find our concentration of OH minus. And we know if we take OH minus and multiply it by H3O plus, that's going to give us 1 times 10 to the negative 14th molar. So to solve for the OH minus, we just divide both sides by the H3O plus. When we do that, that gives us OH minus equals 1 times 10 to the negative 14th molar divided by the H3O plus. And so we can now plug in our numbers. 1 times 10 to the negative 14th molar divided by 2.0 times 10 to the negative 14th molar. And that should tell us our concentration of OH minus. So when you plug these into your calculator, and I'm going to suggest putting parentheses around these as you're dividing, that just tends to come out better. You should get 5 times 10 to the negative 3rd molar. I would go ahead and try that, because if you're not getting that, you're not putting these in correctly, and I just found a mistake right here. It's raised to the negative 12th. I put negative 14th, so make sure you change that in your notes. So, that being said, right, do try this and double check that you can put everything in. If you have any problems, please come see me.